So problem 4.4, you can see it on the screen here. It is basically a derivation which shows that the optimal control problem, or the LQR problem, with finite horizon t could be solved by solving the Riccati differential equation and choosing the optimal control input u as this based on the solution P to the Riccati differential equation. So we'll do it in a slightly different manner than in the solutions given. So we will basically not use this suggestion of u, although we will use this fact here. So let's first write down what the optimal cost is. So given a trajectory in x and in u, so I use this notation to talk about the trajectory x of t for t between 0 and t, and similarly this is the input trajectory for t going between 0 and t. So if I define for a given state trajectory and an input trajectory cost like this, we can then write the LQR problem as follows. So search over all possible input trajectories and minimize this cost subject to these constraints. So that's the LQR problem. Now, before we jump into the solution, we will use the fact provided in the question, which is that if we differentiate x of t transposed p of t x of t, we obtain, now I will suppress the dependence on t for having a compact notation. We have x dot transposed px plus x transpose p dot x plus x transpose p x dot. Now we can substitute the dynamics here and get x transpose a transpose plus u transposed p transposed px plus x transpose p dot x as it is, and x transpose p ax plus pu. So that is nothing but x transposed. Now I will collect all the x transpose ax type terms together. So x transpose ap plus p dot, so I have considered this term, and this term now, plus pa x, and what is left is this term and this term. So plus u transposed p transposed px plus x transpose pbu. Now again, because this is a scalar, the transposed of a scalar is the scalar itself, and the transposed of this is the other term. So this is equal to transpose ATP plus P dot plus PA x plus 2 x transposed PBU. Now if we integrate both sides, so this, remember, here on the left hand side we have d by dt of x transposed px. Now if we integrate both sides from 0 to t, we obtain xt transposed pt xt, where this subscript t denotes x evaluated at time t, p evaluated at time t, and so on, minus x0 transposed p0 x0 is equal to integral 0 to t x transposed, I just write this again, dt. So this is true. This is true for any trajectory p of t that is smooth or that is differentiable, because we've basically just used the chain rule and nothing else, and then we've used basically then we've just integrated both sides. So this holds for any trajectory p of t that is smooth or that is differentiable for this to be defined. Now we keep that in mind. Now we add and subtract to our cost v the left, so this the left hand side and the right hand side. So v of x comma u is nothing but v of x comma u. We add the right hand side and subtract the left hand side. Yeah, that's that. So this part will evaluate to 0 because this is equal to this. So now we can write down explicitly the v, which is 0 to t x transpose qx plus u transpose ru, and combine these two integrants in a single integral sign to get ATP plus PA plus P dot 2x transpose PBU TT minus T transpose PXT minus transpose P0 X0, and plus we have the final cost. Here I can write x t transposed s xt. Now just combining again the terms together, we get x transposed t plus x transposed S minus P, I forgot a T here, X plus X0 transposed P0 X0. So note what we have here. We have that V can be represented in this form where P, or rather the trajectory P, is any trajectory that is differentiable or smooth or has a P dot. So that's what we have, and this holds for any x and u that are compatible with each other, meaning that they satisfy the dynamics x dot equal to ax plus pu, and x at time 0 is x0. Now we can pick therefore a p trajectory that satisfies the Riccati differential equation, which is that minus p dot is ATP plus PA PB R inverse P transpose P plus Q, and P at time t equal to S. Now because this box, this V of XU equal to this holds for any P, we can choose whatever P we want that is differentiable. So we pick a P that solves the Riccati differential equation, because of which then this term, which is P dot plus ATP plus PA plus Q, will be equal to, so if you then have a closer look at this equation, we have, if we shift P dot here and move this term on the other side, we would have that this term is equal to this PBR inverse B transpose P. So that's what we will do. Additionally, because of the boundary condition, this term will vanish. So we will eventually get V of x comma u equal to x transpose. Now because ATP plus PA plus P dot plus Q is equal to PB R inverse B transpose P x, because we choose a P that solves the Riccati differential equation, and we have the other terms as it is, which is 2x transpose PB u dt. Oh, there is an additional u transpose ru dt plus x0 transpose p0 x0. Now at this point you should recognize this thing from problem 4.3 or even 4.2. We can write this thing as 0 to t x transposed u transposed PB R inverse P transpose P, PB R and R times x and u dt, plus we still have this x0 transposed p0 x0 as it is. Now at this point I recommend that you try and show that this is positive semi-definite. For this you will need the sure complement, but you will have to modify it to accommodate for non-strict inequalities, and I recommend you to try that, and also find a u that minimizes this cost. We will instead use a different route and write this as, so this is still the same, we can write it as x transpose PB R inverse plus U times R times R inverse P transpose P x plus U dt, and we still have this term here. So what we have is V, the cost, is given by this expression. Now note that R is positive definite from the LQR problem, and therefore V transpose RV is always greater than 0 for all V in Rn except 0, and V transpose RV is equal to 0 if and only if V is 0, and therefore we have that the integrand is positive, or rather non-negative, and integral of a non-negative function is also non-negative. So we have a lower bound on V. So we have V of is lower bounded by x0 transpose p0 x0, because this is something positive. This whole thing is something positive that is added to x0 transpose p0 x0, and therefore this is a lower bound on V. Now we can even propose a u. Also we have, if u is minus R inverse P transpose Px, then the integrand is 0 and we have that x0 transpose p0 x0 is equal to, let's call this u star, is equal to p of x and u star. So what we have is that we have a lower bound on the cost, and we have a u that achieves this lower bound, and therefore we have basically solved the optimal control problem, in that you cannot have any other u that is giving you a value of v smaller than p0 x0, and we have a u that achieves this smallest value. So we have basically solved the LQR problem, in that if we first solve the Riccati differential equation to get a p of t, then we have a lower bound. This implies that we have a lower bound on our cost for any compatible trajectories x and u. By compatible, I just repeat, I mean trajectories that are compatible with the dynamics x dot equal to ax plus bu and the initial condition x0. We have this lower bound, and then if we specify u star of t equal to minus r inverse p transpose p of t x of t, we can reach this lower bound. Is equal to this one, and yeah, that is basically the solution to problem 4.4. Yeah, thanks a lot. That's it for this problem.